Hello everyone, today we are talking about Transmon Qubit. Transmon Qubit is a kind of superconducting qubit which is a very active field of research today. The motivation of superconducting qubit has developed since 1980s, and the idea is to use macroscopic quantum effect. Typically, there are Cooper pairs acting as charge carriers and work at low temperature. The string kind of superconducting qubit as we've already known: charge qubit, phase qubit, flux qubit. Charge qubit was first proposed in 1997, flux qubit in 1999, and phase qubit in 2001. But as the techniques developing, there are more qubits developed based on these three kinds of qubits, such as fluxinium in 2009, Transmon in 2007, Xmon in 2013, and contronium in 2007. Transmon is what we are going to discuss here. Its full name is Transmission line shunted plasma oscillation qubit. Transmon is based on charge qubit or Cooper pair box. As we've already known, a Cooper pair box is a Josephson junction in series with a capacitor. The Josephson junction has some capacitance Cj and Josephson energy Ej. Here is this Hamiltonian and it works as a region Ej over Ec is much smaller than 1. So the system deviates from a harmonic oscillator. We control the voltage to set the charge and control the qubit, and work near the so-called sweet spot to reduce the effect of charge dispersion. We know that the charge dispersion is uncertain and unknown, and we don't want to get affected by it. Here is the so-called sweet spot. And near this spot, the energy varies little with charge, so it gets less affected. However, if you have a larger charge dispersion, the energy is still affected, so dephasing may happen there. But we can see that as Ej over Ec increases, the E to N pattern becomes flat and the energy is less likely to be affected by the charge dispersion. So we can make use of this effect. This is the motivation of Transmon. But when we consider this, we immediately meet a problem. We can see from the figures that when Ej over Ec becomes very large, the energy level difference between 0, 1 and 1, 2 states become very close. This means the system becomes more like a harmonic oscillator. This means that when we give an excitation signal, the system don't just change between 0 and 1 state, but it can go all the way up to 2, 3, and greater number states. So we can't just select 0 and 1 state to form a qubit, as we do for Cooper pair box. But we discovered that the sensitivity to dispersive charge decreases exponentially with Ej over Ec, while anharmonicity only decreases algebraically, as these two formulas show. So we can manage to find a region where we are still able to control, but less affected by dispersive charge. So how do we do that? Well, we can rearrange the Hamiltonian under the limit of Ej much greater than Ec, and we can get this formula. This is very similar to Jenner's common Hamiltonian using cavity's QED. So we can make an analog to that. Cavity QED describes an atom coupling to the electromagnetic field in a cavity. The cavity has some oscillation modes which correspond to some frequency, and the atom has its own energy levels. The atom may or may not absorb a photon and go to the excited state or emit a photon to go to the ground state. Adjusting the cavity affects the atom state. We can map this to Transmon. The qubit is like the photon. The qubit is like the atom, and the cavity is represented with some control. like some microwave pulse controlled by transmission line resonator, which shows up here. This is a Transmon circuit. The large EJ over EC is not achieved by fabricating the Josephson junction, but by paralleling a very large capacitor, CB, with a Josephson junction. So the difference between Transmon and Cooper pair box is just like here a CB is parallel. By coupling the qubit with the transmission line resonator, we can operate the qubit. And still, Vg is used to set to the sweet spot. Such circuits need to work at dispersive limit, where the transmon frequency is detuned far from the cavity frequency. This is because if we look at the effective Hamiltonian here, this term chi is related to the coupling between qubit and the cavity. If it's important, the qubit can go to larger number states and make our calculations based on a mass. It can go to n is greater than 1, like n equals 2, 3, 4 states, and that is not good. So we make the detuning here to be large. The detuning is represented by the delta here. So chi becomes small, and the state is mainly in 0 and 1 state. Here is some pictures of the device. We need to use microwave pulse to control it, so we use transmission line resonator. As a transmission line resonator is just like an oscillation qubit, an oscillation circuit working at microwave frequency. It's proper for this function. The control and readout are nothing special. We can generate a pulse at frequency omega r plus or minus chi to make a projective measurement, and we can use any other pulses we want to control, as we learned for other qubit systems. It's worth pointing out that Transmon is in some ways between charge and phase qubit, but different from them. The Hamiltonian of Transmon is the same as that of charge qubit, but work at the opposite extreme EJ over EC limit. The charge qubit controls by voltage, but the Transmon controls by microwave pulse. As for with phase qubit, the Transmon has different physics for Hamiltonian with it, but they both work at the region EJ over EC is much greater than 1, and they both use microwave control. The Transmon qubit was developed for longer coherence time. If we look at this, it has reached nearly 100 microseconds. This is a relatively good result compared to some other circuit qubit here, like flux qubits, Fluxinium, Xmon, and here is a picture showing more experimental results. However, there is a difficulty for Transmon and also for many other qubits, that the device and therefore the coherent time result is difficult to duplicate from one to another. You may get this very good result of coherence time for this device, but for another device you may not get the same good result. Transmon qubit is very widely used for quantum computation because it's relatively easy to build multi-qubit systems with it. This is a picture of a 20-qubit chip based on Transmon, which was fabricated in 2019. And also in 2019, Google claimed quantum supremacy, and they used a processor of 54 Transmon qubits. It's also based on Transmon Qubit. Transmon is a very promising system for future development of quantum computation. That's all I have here. Transmon has been proposed for over 10 years and has demonstrated great potential. I hope this gives you a sense of Transmon Qubit. Thank you for listening.